The most distant galaxy we can possibly observe lies approximately 46.5 billion light-years away from Earth. Light from that galaxy has been traveling toward us for 13.4 billion years, nearly the entire age of the universe itself, carrying information about cosmic conditions when the universe was barely 400 million years old. Yet that galaxy, which emitted the light we detect today, now resides 46.5 billion light-years distant. Mathematics seems impossible. How can light travel for 13.4 billion years and cross a distance of 46.5 billion light-years? How can the observable universe stretch 93 billion light-years in diameter when the universe is only 13.8 billion years old? This apparent paradox has confused students, challenged intuition, and prompted countless questions since astronomers first recognized that the universe expands. The answer reveals profound truths about the nature of space itself, the difference between distance as we experience it locally and distance across cosmic scales, and the strange implications of living in an expanding universe where the fabric of space-time itself stretches, carrying galaxies along with it while light struggles across the growing void between them. The confusion arises from assuming space is static, a fixed backdrop against which objects move. In our everyday experience, this assumption works perfectly. The distance between cities remains constant. Light travels at 300,000 kilometers per second, and in 1 year, it covers 9.46 trillion kilometers 1 light year. If something is 10 light years away, light takes 10 years to travel from there to here, and the distance is 10 light years. Simple, intuitive, and completely wrong when applied to cosmological scales. The universe is not a static stage. Space itself expands, and this expansion has been occurring since the Big Bang 13.8 billion years ago, when we observe a distant galaxy. The light we receive began its journey billions of years ago when that galaxy was much closer to us. As the light traveled toward us, space itself stretched, carrying the emitting galaxy farther away and stretching the light's wavelength, shifting it toward redder wavelengths. By the time the light reaches our telescopes, the galaxy that emitted it lies at a vastly greater distance than when the emission occurred. This expansion means that distance in cosmology requires careful definition. The light travel time, how long light has been traveling, differs from the current proper distance, how far away the galaxy is right now. These two distances are not equal in an expanding universe. Light from a galaxy 13 billion light-years away by light travel time has crossed 13 billion light-years worth of space, but during those 13 billion years, the universe expanded. So the galaxy now lies perhaps 30 or 40 billion light-years distant measured in today's coordinates. The observable universe, the spherical region around Earth from which light has had time to reach us since the Big Bang, extends to a co-moving distance of about 46.5 billion light-years in all directions. This defines a sphere 93 billion light-years in diameter. Everything inside this sphere is theoretically observable, though in practice, we cannot see beyond the cosmic microwave background at 13.8 billion years ago when the universe became transparent. Everything outside this sphere lies beyond our cosmic horizon. Light from those regions has not had time to reach us yet. The size of the observable universe depends critically on the universe's expansion history. If the universe expanded at a constant rate, the relationship between age and size would be simpler. But the universe's expansion has not been constant. It began with a brief period of exponential inflation, expanding faster than light by enormous factors in a tiny fraction of a second. After inflation ended, expansion slowed as matter's gravity pulled back against the expansion. Then, approximately 5 billion years ago, dark energy began dominating, causing expansion to accelerate again. This complex history means calculating the size of the observable universe requires integrating the expansion rate over the universe's entire history. The observable universe's finite size does not mean the universe itself is finite. The universe might be infinite, extending forever in all directions beyond our horizon. We cannot observe these distant regions because light has not had time to reach us, but they presumably exist, containing galaxies, stars, and perhaps even observers who see their own observable universe that overlaps only partially or not at all with ours. Alternatively, the universe might be finite but unbounded, curved back on itself like the surface of a sphere, such that traveling far enough in one direction returns you to your starting point. Understanding why the observable universe is 93 billion light-years across despite being only 13.8 billion years old requires understanding general relativity and cosmic expansion, learning how astronomers measure distances to remote galaxies, comprehending the cosmic microwave background and what it reveals about early universe conditions, grasping how dark energy accelerates expansion, and appreciating the observational evidence supporting this cosmic model. It requires distinguishing between different distance definitions, understanding how light behaves in expanding space, and recognizing that cosmic horizons impose fundamental limits on what we can observe. Tonight, we will explore these concepts from foundations to frontiers, building understanding of spacetime expansion, cosmic history from the Big Bang through today, distance measurement techniques spanning megaparsecs to gigaparsecs, the evidence from cosmic microwave background observations, the role of dark energy in cosmic acceleration, the geometry of space itself, and what all this means for our place in the cosmos. We will discover that the universe is stranger and larger than it appears, that 13.8 billion years has been sufficient for space to stretch to 93 billion light-years because space itself expands, and that the observable universe's edge marks not a physical boundary but a horizon imposed by the finite speed of light and the finite age of the cosmos. Before we begin this journey across cosmic scales, if you are fascinated by cosmology, the expansion of space, and the fundamental limits on observation, subscribe and give this video a thumbs up. And here is a question: if you could send a signal to observers in a galaxy at the edge of our observable universe, knowing they would receive it billions of years in the future when they might no longer exist, what message would you send? Comment below. I will pin the most thought-provoking answer. The universe stretches across 93 billion light-years, filled with 2 trillion galaxies, each containing billions or hundreds of billions of stars, all embedded in expanding space that carries them ever farther apart while light races across the growing void. Understanding why this size is possible in only 13.8 billion years unlocks one of cosmology's deepest insights. Now let's begin. Space expands. The foundation for understanding the observable universe's size is recognizing that space itself can expand, stretch, grow. This is not a metaphor or approximation but a precise statement about the geometry of spacetime described by Einstein's general theory of relativity. Space is not a fixed, absolute backdrop, an Newtonian container where objects move but which remains unchanging. Space is dynamic, its geometry evolving according to the distribution and flow of energy and matter within it. General relativity, published by Einstein in 1915, revolutionized our understanding of gravity and spacetime. The theory describes gravity not as a force acting across empty space, but as the curvature of spacetime itself caused by the presence of mass and energy. Massive objects like stars and planets warp the spacetime around them, and this warping dictates how other objects move. The famous summary is matter tells spacetime how to curve, and spacetime tells matter how to move. Einstein's equations allow spacetime itself to change, to expand or contract. In 1922, Russian physicist Alexander Friedmann found solutions to Einstein's equations describing a universe that is not static but expanding uniformly in all directions. Independently, Belgian physicist Georges Lemaitre proposed in 1927 that the universe began in a hot dense state and has been expanding ever since. These theoretical insights preceded observational confirmation. Edwin Hubble provided that confirmation in 1929. Observing galaxies with the 100-inch Hooker telescope at Mount Wilson Observatory, Hubble measured their distances using variable stars called Cepheids whose intrinsic brightness could be calibrated. He also measured the galaxies' redshifts, the stretching of their light toward longer, brighter wavelengths. Hubble found that more distant galaxies exhibit larger redshifts, moving away from us faster. The universe is expanding. This expansion is not galaxies moving through space like shrapnel from an explosion. It is space itself expanding, carrying galaxies along with it. Imagine the surface of a balloon with dots marked on it representing galaxies. As you inflate the balloon, the surface expands, and every dot moves away from every other dot. No dot is at the center of the expansion. From each dot's perspective, all other dots recede. The galaxies are not moving through space. Space is expanding between them. The expansion rate is characterized by the Hubble constant, denoted h, which expresses how fast space expands. The current best measurements place h at approximately 70 kilometers per second per megaparsec. This means that for every megaparsec 3.26 million light-years of distance, space expands such that galaxies appear to recede at 70 kilometers per second. A galaxy 10 megaparsecs away recedes at 700 kilometers per second. 100 megaparsecs away recedes at 7,000 kilometers per second, and so on. At large enough distances, recession velocity exceeds the speed of light. A galaxy 4,286 megaparsecs 14 billion light-years away recedes at 300,000 kilometers per second, the speed of light. Galaxies beyond this distance recede faster than light. This does not violate relativity because the galaxies are not moving through space faster than light. Space itself expands, and there is no limit on how fast space can expand. Special relativity's speed limit applies to motion through space, not to the expansion of space itself. This superluminal recession has profound implications. Light emitted from galaxies receding faster than light initially moves away from us, carried by the expansion. If expansion were constant, this light would never reach us. However, as light travels, it finds itself in regions where space expands more slowly relative to its position, and eventually, it can make progress toward us. Whether light from a distant galaxy ever reaches us depends on the entire expansion history of the universe, not just the recession velocity at the moment of emission. The expansion of space stretches not only the separations between galaxies but also the wavelengths of light traveling through space. Light emitted at a particular wavelength lambda_emit arrives at Earth with a longer wavelength lambda_obs. The ratio lambda_obs lambda_emit defines the redshift parameters z equals lambda_obs lambda_emit lambda_emit. For small velocities, redshift relates simply to recession velocity through the Doppler effect, but for large cosmological distances, redshift reflects the integrated expansion of space over the light's travel time. A galaxy with redshift z equals 1 emitted its light when the universe was half its current size. Wavelengths have been stretched by a factor of 2. A galaxy at z equals 2 emitted light when the universe was 1/3 its current size. The highest redshift galaxies observed have z greater than 10, meaning the universe was less than 1/10 its current size when the light was emitted. The cosmic microwave background has a redshift of approximately z equals 1,100, emitted when the universe was about 1,100 times smaller than today. The expansion is uniform and isotropic on large scales, meaning space expands at the same rate everywhere and in all directions. This is observed fact, confirmed by the uniformity of the cosmic microwave background and the large-scale distribution of galaxies. On smaller scales, expansion is not noticeable. Gravitationally bound systems like galaxies, galaxy clusters, atoms, and humans do not expand because their internal forces, gravity, electromagnetism, vastly overpower the expansion. Only on scales of hundreds of millions of light-years, where structures are not gravitationally bound, does expansion dominate. The expansion started from a hot, dense state called the Big Bang. Extrapolating backward in time, as space contracts, matter and energy become denser and hotter. At 13.8 billion years ago, the universe was infinitely dense and hot according to naive extrapolation, though quantum gravitational effects likely prevent true infinity. This moment marks the beginning of the universe as we understand it, not an explosion into pre-existing space, but the expansion of space itself from an initial state. The Big Bang is often misunderstood as an explosion occurring at a point in space, with galaxies flying outward from that center. This is incorrect. The Big Bang occurred everywhere simultaneously. Every point in space today was present at the Big Bang, just vastly closer together. There is no center of the universe, no special location from which everything expands. Every observer sees themselves at the center of their observable universe, with galaxies receding in all directions. Visualizing cosmic expansion challenges intuition. One analogy is the raisin bread dough model. As bread dough rises, raisins embedded in it move apart, not because they move through the dough but because the dough expands, carrying them along. Another analogy is the expanding rubber sheet, though this is less accurate because it suggests a two-dimensional space embedded in three dimensions. Whereas actual space expands without being embedded in any higher dimensional space, the expansion rate has not been constant over the universe's history, in the first tiny fraction of a second. The universe underwent exponential inflation, expanding faster than light by enormous factors. After inflation, expansion slowed due to matter's gravitational attraction. Around 5 billion years ago, dark energy began dominating, causing expansion to accelerate. The current expansion rate is faster than it was 5 billion years ago and will continue accelerating indefinitely if dark energy remains constant. The combination of finite age and accelerating expansion creates the observable universe's size. If expansion had been constant at today's rate, the observable universe would be smaller, roughly 13.8 billion light-years in radius. If expansion had been much slower early on, the universe would be smaller still. But early expansion was faster immediately after inflation, then slowed, so light could make progress across space. This complex history results in the observable universe radius of 46.5 billion light-years. To understand how we arrive at 46.5 billion light-years requires integrating the expansion rate over cosmic history. The scale factor AT describes how the universe's size changes with time, normalized so at t equals 1 today. At earlier times, at t was smaller. The scale factor relates to redshift by equals 1 z. The co-moving distance to a galaxy at redshift z is calculated by integrating the inverse of the scale factor's time derivative, weighted by the speed of light, from the emission time to today. This integral accounts for how much space the light crossed, taking into account that space was expanding while the light traveled. The result for the most distant observable objects, those at z approaching infinity, the Big Bang itself, is approximately 46.5 billion light-years in co-moving coordinates. Co-moving means the distance measured in coordinates that expand with space, representing the proper distance as it is right now. The counterintuitive result, that light can travel for 13.8 billion years and cover 46.5 billion light-years, rises because space expanded while the light traveled. Early in the journey, when the universe was smaller and denser, the light covered less co-moving distance per unit time because space was expanding faster relative to the light's progress. As expansion slowed before dark energy dominated, light made better progress. The total co-moving distance depends on the integral over the entire journey, not simply on multiplying light speed by time. Understanding that space expands is the critical conceptual leap. Once you accept that the geometry of space itself is dynamic, that distances between galaxies increase not because galaxies move but because space grows, the size of the observable universe becomes mathematically predictable and observationally confirmed. The universe is larger than its age in light-years because space has been expanding for 13.8 billion years, stretching early emitted light across ever greater distances, creating an observable region far larger than naive calculations would suggest. Distance definitions. Measuring distance in cosmology is far more complex than measuring distances on Earth or even within the solar system. In an expanding universe, the question "how far away is that galaxy?" has multiple answers depending on what you mean by distance. Cosmologists use several distance definitions, each useful for different purposes. And understanding the distinctions is essential for grasping why the observable universe is 93 billion light-years across. The most intuitive distance definition is proper distance, the distance measured at a specific moment in time using rulers laid end-to-end across space, representing the separation you would measure if you could freeze the universe and measure directly. Proper distance changes as the universe expands. A galaxy with a certain proper distance today had a smaller proper distance in the past and will have a larger proper distance in the future. When cosmologists state the observable universe is 93 billion light-years in diameter, they mean proper distance measured right now. Light travel distance is the distance light has traveled, equal to the speed of light times the time since emission. If light from a galaxy has been traveling for 10 billion years, the light travel distance is 10 billion light-years. This is the distance most people intuitively think of when they hear a galaxy 10 billion light-years away, but it does not represent the galaxy's current separation from us. Light travel distance is always less than proper distance for cosmological objects because space expands while light travels. Co-moving distance is proper distance expressed in coordinates that expand with the universe, factoring out the expansion. Co-moving distance to a galaxy remains constant over time if the galaxy is not subject to peculiar velocities motion through space as opposed to motion with space. The observable universe's radius of 46.5 billion light-years is co-moving distance. Co-moving coordinates provide a convenient framework for describing cosmic structure because they don't change due to expansion. Luminosity distance relates to how bright an object appears compared to its intrinsic brightness. If an object with luminosity L, total energy emitted per second, is at luminosity distance d_L, its observed flux F, energy received per unit area per unit time, is F equals L for d_L squared. In an expanding universe, light not only spreads over increasing area but also gets redshifted, reducing photon energy, and arrives at a slower rate due to time dilation. Both effects make distant objects dimmer, so luminosity distance exceeds proper distance. For a galaxy at redshift z, luminosity distance d_L approximately equals proper distance times 1z. Angular diameter distance relates to how large an object appears on the sky. An object of physical size d at angular diameter distance d_subtends an angle theta equals d_. In a static universe, distant objects appear smaller because they subtend smaller angles. But in an expanding universe, light from distant objects was emitted when the universe was smaller and the object was closer, so very distant objects can appear larger than they would in a static universe. Angular diameter distance initially increases with redshift, reaches a maximum around z approximately equals 1.6, then decreases for higher redshifts. This counterintuitive behavior means the most distant galaxies subtend larger angles than moderately distant galaxies of the same physical size. The relationship between these distances depends on redshift and the universe's expansion history. For small redshifts nearby galaxies, all distance definitions approximately agree. For large redshifts, they diverge significantly. A galaxy at redshift z equals 10 might have a light travel distance of 13.2 billion light-years. Light has been traveling for 13.2 billion years. A proper distance of 30 billion light-years current separation. A luminosity distance of 330 billion light-years how dim it appears, and an angular diameter distance of 2.7 billion light-years how large it appears on the sky. These distances are calculated using the Friedmann equations derived from general relativity, which describe how the universe's scale factor AT evolves with time. The scale factor's evolution depends on the universe's contents, matter including dark matter, radiation, and dark energy. The current standard cosmological model, called lambda-CDM, includes approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. These components have different effects on expansion. Matter's gravity slows expansion. In a matter-dominated universe, expansion decelerates. With the scale factor growing as AT varies as t to thirds, radiation photons and relativistic particles also slows expansion but more strongly. In a radiation-dominated universe, AT varies as t1/2. Dark energy, which has negative pressure, accelerates expansion. If dark energy is the cosmological constant lambda, constant energy density everywhere, the universe eventually expands exponentially, with a t varies as the xpht, where h is the expansion rate. The universe's expansion history divides into epochs dominated by different components. In the first approximately 50,000 years, radiation dominated, and expansion was relatively fast. From approximately 50,000 years to approximately 10 billion years, matter dominated, and expansion slowed. For the past approximately 4 billion years, dark energy has dominated, and expansion has accelerated. This complex history means calculating distances requires integrating through all these epochs. The proper distance to a galaxy at redshift z is given by integrating the speed of light over the time light traveled, accounting for expansion. T_proper equals c asterisk integral from t_emit to t_now of dt of at, converting to redshift as the variable. P_co-moving equals ch asterisk integral from 0 to z of dz where ez equals squared omega_m1 plus e cubed plus omega_r1z plus omega_lambda with omega_m, omega_r, omega_lambda the density parameters for matter, radiation, and dark energy. This integral has no analytical solution for general omega values but can be computed numerically. For the standard lambda CDM model with h approximately equals 70 km per second mpc, omega_m approximately equals 0.3, omega_lambda approximately equals 0.7, the integral yields a co-moving distance to the cosmic horizon z gives infinity of approximately 46.5 billion light-years, or about 14,300 megaparsecs. Why does the integral give such a large result despite finite age? Early in the universe, when the t was small, the integrand dt of at is large, contributing significantly to the total distance. Although the universe was radiation-dominated and expanding fast, light was making progress across space because the expansion rate, while high, was not so high as to prevent light from crossing space. The integral sums contributions from all epochs, weighted by the expansion at each epoch. The role of inflation, which occurred in the first tiny fraction of a second, is sometimes misunderstood in this context. Inflation expanded the universe exponentially by enormous factors, perhaps 1026 or more. However, inflation occurred before any light was emitted that we observe today. The cosmic microwave background, the earliest light we can see, was emitted 380,000 years after the Big Bang, long after inflation ended. Inflation affects the observable universe's size by setting the initial conditions for expansion, not by directly contributing to the light travel distance. Another subtlety involves the particle horizon versus the cosmic event horizon. The particle horizon is the boundary of the observable universe, the distance light could have traveled since the Big Bang. Its radius is approximately 46.5 billion light-years. The cosmic event horizon, relevant in an accelerating universe, is the boundary beyond which events occurring now will never be observable in the future because light from them can never catch up to us due to accelerating expansion. The event horizon is currently about 62 billion light-years away. Distance measurements in cosmology rely on the cosmic distance ladder, a series of techniques calibrated against one another. For nearby objects, parallax apparent shift in position due to Earth's orbit gives direct geometric distances. For more distant stars, standard candles like Cepheid variables whose intrinsic brightness is calibrated provide distances up to approximately 100 million light-years. Type Ia supernovae, even brighter standard candles, extend the ladder to billions of light-years. For the most distant objects, redshift combined with cosmological models infers distance. Each rung of the distance ladder carries uncertainties that propagate to larger scales. Uncertainty in the Hubble constant h, currently debated at the few percent level, creates uncertainty in all distance measurements beyond the local universe. Different techniques for measuring h yield slightly different values, a tension that cosmologists are actively working to resolve. The most distant objects' distances depend on assumptions about dark energy and the universe's geometry, introducing model dependence. Despite uncertainties, the overall framework is robust. The observable universe's size of 93 billion light-years is not a precise measurement but a model-dependent calculation based on well-established physics and observations. The value could be larger or smaller by a few percent depending on exact parameters, but the order of magnitude is secure. The observable universe is definitively much larger than 13.8 billion light-years in radius, and this is a direct consequence of cosmic expansion. Understanding distance definitions clarifies why statements like a galaxy 13 billion light-years away are ambiguous without specifying which distance measure is meant. In popular science, 13 billion light-years away typically means light travel time, indicating light has been traveling for 13 billion years. The galaxy's proper distance is larger, perhaps 30 billion light-years. This distinction is crucial for understanding the observable universe's size and for avoiding paradoxes that arise from conflating different distance measures. Cosmic inflation. The observable universe's vast size connects intimately to cosmic inflation, a brief period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang. Inflation solved several major problems in cosmology while simultaneously explaining why the observable universe is flat, homogeneous, and isotropic on large scales. Understanding inflation is essential for understanding how the universe reached 93 billion light-years in diameter despite being only 13.8 billion years old. The inflationary epoch is hypothesized to have occurred between approximately T-36 and 10 to 30 seconds after the Big Bang, though these timescales are model-dependent. During inflation, the universe expanded exponentially, doubling in size every 10 to 37 seconds or so. Over perhaps 100 doublings, the universe expanded by a factor of at least 1026, meaning a region initially smaller than an atom grew to macroscopic or even astronomical sizes. This explosive expansion dwarfs all subsequent expansion from 10 to 30 seconds to today. Inflation was driven by a scalar field called the inflaton, whose energy density remained nearly constant as the universe expanded, and like matter or radiation, whose densities dilute as space expands. The inflaton's constant energy density created negative pressure that drove exponential expansion. This is analogous to dark energy today, which also has constant energy density and drives accelerated expansion. Though the energy scale of inflation was vastly higher, approximately 1016 compared to dark energy's 1000 electron volts, the inflaton field existed in a false vacuum state, a high-energy metastable state, like a ball perched on a plateau in a potential energy landscape. Quantum fluctuations eventually caused the inflaton to roll off the plateau, transitioning to the true vacuum of lower energy. This transition, called reheating, converted the inflaton's energy into ordinary particles and radiation, heating the universe to enormous temperatures and initiating the hot Big Bang phase that standard Big Bang cosmology describes. Inflation solved the horizon problem. Without inflation, different regions of the observable universe were never in causal contact. They were separated by distances larger than light could travel in the universe's age. Yet these regions have nearly identical temperatures as measured by the cosmic microwave background, differing by only 1 part in 100,000. How could regions that never interacted achieve such uniformity? Inflation solves this by proposing that all observable regions were in causal contact before inflation, allowing them to thermalize. Inflation then stretched this small causally connected region to encompass our entire observable universe and far beyond. Inflation also solved the flatness problem. The geometry of space can be flat Euclidean, closed positively curved like a sphere, or open negatively curved like a saddle. The universe appears extremely flat, with curvature measurements consistent with 0 to within a fraction of a percent. Without inflation, maintaining flatness requires extraordinary fine-tuning of initial conditions. As the universe expands, any curvature becomes more pronounced. A closed universe would recollapse, and an open universe would expand too fast for structure formation. For the universe to be nearly flat today, it must have been incredibly precisely flat initially, tuned to 1 part in 1060 or better. Inflation solves this naturally by expanding space so enormously that any initial curvature becomes undetectable. Analogous to how the surface of a balloon appears flat locally even though it's globally curved. Even if the universe started with significant curvature, inflation stretched space so much that the observable universe became flat to a high degree. Measurements from the cosmic microwave background confirm the universe's flatness, supporting inflation. Inflation also addressed the monopole problem. Grand unified theories of particle physics predict that topological defects like magnetic monopoles should have been produced in the early universe in enormous quantities. These monopoles would dominate the universe's mass density, yet none have been observed. Inflation solves this by diluting any monopoles produced before inflation to undetectable densities, spreading them across the inflated universe such that the observable region likely contains none. Beyond solving these problems, inflation makes a remarkable prediction. Quantum fluctuations in the inflated field during inflation would be stretched to macroscopic scales, creating slight density variations in the early universe. These fluctuations seeded structure formation, growing through gravitational collapse into galaxies, clusters, and the cosmic web. The amplitude and statistical properties of these fluctuations are calculable and match observations of the cosmic microwave background's temperature fluctuations with impressive precision. The inflationary paradigm is not without controversies. Multiple inflation models exist, differing in the inflatant's properties and the mechanism hinting inflation. Some models predict eternal inflation, where inflation never ends globally, but only ends in localized pockets like our observable universe, creating a vast multiverse of bubble universes. This multiverse hypothesis is philosophically contentious and may not be testable. Critics argue inflation is not falsifiable if any failure to match predictions can be accommodated by adjusting the inflatant potential. Alternatives to inflation have been proposed, including cyclic models where the universe undergoes repeated cycles of expansion and contraction, and bounce cosmologies where the Big Bang is replaced by a bounce from a preceding contracting phase. These alternatives aim to explain the same observations inflation addresses but have not achieved the same level of acceptance, partly because they lack inflation's elegant resolution of multiple problems simultaneously and partly because inflation's predictions have been confirmed observationally. Observational evidence for inflation comes primarily from the cosmic microwave background. The Planck satellite, which mapped the CMB temperature and polarization with extraordinary precision, found the distribution of temperature fluctuations matches inflationary predictions. The fluctuations or Gaussian statistical distribution follows a bell curve, adiabatic density and temperature fluctuations related in a specific way, and nearly scale invariant amplitude similar at different scales, all hallmarks of inflation. The spectral index of fluctuations, measured to be approximately 0.96, deviates slightly from exact scale invariance in the direction inflation predicts. Inflation also predicts gravitational waves produced by quantum fluctuations in spacetime itself during inflation. These primordial gravitational waves would imprint a specific pattern in the CMB's polarization, a curl-like pattern called B-mode polarization. Detecting this signal would provide smoking gun evidence for inflation and constrain the energy scale at which inflation occurred. Several experiments, including BICEP and Planck, have searched for B-modes, finding upper limits but no definitive detection. The search continues with upcoming ground-based and satellite missions. How does inflation relate to the 93 billion light-year observable universe? Inflation did not directly create the observable universe's size. Rather, it set the stage by creating a vast, flat, homogeneous region from which our observable universe is a tiny part. The region inflated to become our observable universe was smaller than a proton before inflation and inflated to perhaps a few centimeters, encompassing the material that would become billions of galaxies. This tiny pre-inflation region was causally connected, explaining uniformity. After inflation ended, normal expansion took over. The universe was radiation-dominated, then matter-dominated, then dark energy-dominated, with expansion rates governed by the Friedmann equations. Over 13.8 billion years, the region inflated to centimeters expanded further to billions of light years, not through inflation but through normal expansion. The integration of expansion rates over cosmic history yields the 46.5 billion light-year co-moving radius. Without inflation, the observable universe would be much smaller. Extrapolating back without inflation, the observable universe's material would have emerged from regions that were never causally connected, making it impossible to explain the CMB's uniformity. The observable universe's size of 93 billion light-years is consistent with inflation plus 13.8 billion years of post-inflationary expansion. But it would be inconsistent with 13.8 billion years of expansion alone starting from Planck scale. Initial conditions without inflation. Inflation also explains why the observable universe is likely a tiny fraction of the whole universe. If inflation expanded a microscopic region to macroscopic or even light years in size, and our observable universe 93 billion light-years derives from a centimeter-scale region of that inflated space, then the total inflated region is vastly larger than observable, perhaps infinite. We see only a tiny patch, with most of the inflated universe lying beyond our cosmic horizon, forever unobservable. This raises the question of what lies beyond the observable universe. If inflation produced a vast homogeneous region, then beyond our horizon lie more galaxies, stars, and large-scale structures statistically similar to what we observe. Alternatively, if inflation is eternal, creating a multiverse, regions beyond our horizon might have different physical properties, different vacuum states, different physical constants, making them radically unlike our observable universe. These possibilities remain speculative, but illustrate how inflation expands not just space but also conceptual possibilities for the universe's full extent. Inflation remains the leading paradigm for early universe cosmology, supported by compelling theoretical motivations and strong observational evidence. While details remain to be worked out and alternatives continue to be explored, inflation successfully explains the observable universe's flatness, uniformity, and size in a coherent framework. Understanding inflation is understanding why the universe could grow from quantum scale to 93 billion light-years in 13.8 billion years. A growth driven first by exponential inflation and then by 13.8 billion years of standard expansion, creating the vast cosmos we observe. Expansion history. The observable universe's size is the cumulative result of 13.8 billion years of expansion, but that expansion has not been uniform. The universe's expansion rate has changed dramatically over cosmic history, influenced by the relative contributions of radiation, matter, and dark energy. Understanding this history is crucial for calculating how light from distant galaxies reaches us and why the observable universe is 93 billion light-years across rather than 13.8 billion light-years. The expansion rate at any given time is described by the Hubble parameter Ht, which varies over cosmic history. Today's value is the Hubble constant h approximately equals 70 km per second mpc, but in the past, Ht was much larger. The evolution of Ht is governed by the Friedmann equations, which relate the expansion rate to the universe's energy density. The first Friedmann equation is h squared equals hg at 3 rho kT squared, where g is Newton's gravitational constant, rho is the total energy density, k is the spatial curvature zero for a flat universe, and a is the scale factor. The energy density rho includes contributions from matter, radiation, and dark energy, each diluting differently as the universe expands. Radiation, photons, and relativistic particles has energy density scaling as rho underscore r varies as e because the number density dilutes as a cube volume increases, and each photon's energy decreases as e due to redshift. Matter, both ordinary and dark, has energy density scaling as rho underscore n varies as a cube, diluting only from volume increase since matter particles are non-relativistic. Dark energy, if it is a cosmological constant, has constant energy density rho underscore lambda equals constant, not diluting at all. In the earliest moments, radiation dominated because its higher power of E made it dominant when it was very small. The radiation-dominated epoch lasted until approximately 50,000 years after the Big Bang. Redshift Z approximately equals 3,400. During this time, the universe expanded rapidly, with the scale factor growing as At varies St1/2. The rapid expansion reflected the high energy density of radiation. At 50,000 years, matter's energy density equaled radiation's, marking matter-radiation equality. After this, matter dominated, and expansion slowed. From approximately 50,000 years to approximately 10 billion years, the approximately equals 0.3, the universe was matter-dominated, with a t varies as t to thirds. Gravity from matter decelerated the expansion, causing the expansion rate ht to decrease steadily. Around 10 billion years after the Big Bang, dark energy began to dominate. Dark energy's constant density became larger than matter's diluted density as the universe expanded. In the dark energy-dominated era, which continues today, expansion accelerates. The Hubble parameter HT decreases more slowly and will asymptotically approach a constant value, with a t varies as the xph_lambda t, exponential expansion. This complex history means the expansion rate HT was highest in the early radiation-dominated epoch, decreased through the matter-dominated epoch, and now increases slightly as dark energy drives acceleration. The peak expansion rate occurred at the end of inflation, vastly higher than any subsequent expansion. But inflation's contribution to the observable universe's size is indirect, setting initial conditions rather than directly contributing to distances light traveled. Calculating the observable universe's size requires integrating the expansion over all these epochs. The co-moving distance light traveled from time t_emit to today t is v_co-moving equals c integral t_emit to t dt at, converting to redshift z as the integration variable using dz equals hca dz. And other relations, d_co-moving equals c h integral 0 to z dz at omega_m1 z cubed plus omega_r1 plus z plus omega_lambda 1/2. For z gives infinity the Big Bang, this integral yields approximately 3.3 times the Hubble radius. C h is approximately equals 14,000 mpc equals 46 billion light-years for standard cosmological parameters. The factor of 3.3 rises from integrating over the entire expansion history. In the radiation-dominated era, the integrand is largest because at is small, meaning dt of at is large, contributing significantly to total distance. The matter-dominated era contributes less per unit redshift because expansion was slower. The dark energy-dominated era contributes least because expansion is fast again, but there is relatively little time in this era compared to earlier epochs. The expansion history also determines look-back time, the time since light was emitted as a function of redshift. Light from a galaxy at redshift z equals 1 has been traveling for about 8 billion years look-back time, but the galaxy is now about 10 billion light-years away in proper distance due to expansion. Light from z equals 10 has been traveling for 13.2 billion years, but the galaxy is approximately 30 billion light-years away now. The relationship between look-back time and proper distance is nonlinear, with proper distance increasing faster than look-back time due to expansion. The age of the universe is determined by integrating backward from today to the Big Bang, finding when a t equals 0. The age is t equals integral 0 to infinity dz at 1 zhc for standard lambda CDM parameters. This integral yields t approximately equals 13.8 billion years. The age depends on the same cosmological parameters governing the universe's size, so measurements constraining age also constrain size. Observations of the cosmic microwave background, boron acoustic oscillations, and distant supernovae all provide data that fit the lambda CDM model, yielding consistent values for age and size. The transition from deceleration to acceleration approximately 5 billion years ago has important implications. Before this transition, expansion was slowing, making it easier for light to catch up. After the transition, expansion accelerates, making it harder. Galaxies beyond the current cosmic event horizon about 62 billion light-years away are receding faster than light can make progress toward us, so we will never see them as they appear now, though we can see them as they were in the past when they were closer. The future of expansion depends on dark energy's nature. If dark energy is the cosmological constant energy density, expansion will continue accelerating forever, eventually approaching exponential expansion. Galaxies beyond our local group will accelerate away, eventually receding faster than light and disappearing from view beyond the cosmic event horizon in 100 billion years. Only our local gravitationally bound cluster will remain visible. The rest of the universe will have receded beyond observability. Alternatively, if dark energy evolves with time, the future could differ. If dark energy density increases phantom energy, acceleration could strengthen, leading to a big rip where expansion becomes so rapid that it tears apart galaxies, stars, planets, atoms, and eventually spacetime itself. If dark energy density decreases and becomes negative, expansion could reverse, leading to a big crunch where the universe recollapses. Current observations suggest dark energy is consistent with a cosmological constant, implying eternal accelerated expansion. But uncertainties remain. The expansion history also affects structure formation. Galaxy formation requires dark matter halos to collapse gravitationally, accumulating gas that form stars. This process is most efficient during the matter-dominated era when expansion is slowing. In the dark energy-dominated era, acceleration works against gravitational collapse on large scales, effectively shutting down the formation of new large-scale structures. The largest structures we observe, galaxy superclusters, form during matter domination. No larger structures will form in the future due to dark energy's acceleration. Observations of the expansion history come from multiple sources. Type Ia supernovae, which have calibrated peak brightness, serve as standard candles to measure distances to high redshift galaxies, tracing the expansion history out to z approximately equals 1. The discovery in 1998 that distant supernovae are dimmer than expected, indicating larger distances than predicted by decelerating models, provided the first evidence for accelerating expansion and dark energy, winning the 2011 Nobel Prize. Baroid acoustic oscillations BAO, a pattern of galaxy clustering imprinted by sound waves in the early universe, provide a standard ruler to measure distances to galaxies at various redshifts. BAO measurements trace expansion history from z equals 0 to z approximately equals 2, complementing supernova data. The cosmic microwave background provides constraints on the expansion history through its detailed temperature and polarization patterns, effectively measuring expansion from z equals 1100 to today. Combining these observations with models yields the lambda-CDM cosmological parameters. The universe's composition is approximately 68% dark energy, 27% dark matter, and 5% ordinary matter. The Hubble constant is h approximately equals 70 km per second mpc, with ongoing debate about the exact value. The universe is spatially flat k equals 0 within measurement precision. These parameters, plugged into the Friedmann equations, predict the observable universe's size of 93 billion light-years, consistent with the universe's age of 13.8 billion years. The expansion history reveals that the observable universe's size is not simply age times speed of light, but rather the result of a complex interplay of epochs with different expansion rates. Radiation domination expanded the early universe rapidly. Matter domination slowed expansion, allowing light to make progress across space. Dark energy domination accelerates expansion again, limiting how much additional universe will come into view. The cumulative effect over 13.8 billion years, integrated through all epochs, produces the 93 billion light-year diameter we calculate. A size entirely consistent with known physics and confirmed by multiple independent observations. Measuring the cosmos, determining that the observable universe is 93 billion light-years across, requires measuring distances to extremely remote objects, a task that pushes observational astronomy to its limits. The cosmic distance ladder, a series of overlapping measurement techniques each calibrated against the previous, extends from nearby stars to the edge of the observable universe. Understanding how astronomers measure cosmic distances reveals both the power and the limitations of our knowledge about the universe's size. The first rung of the distance ladder is stellar parallax, the apparent shift in a star's position due to Earth's orbit around the Sun. As Earth moves from one side of its orbit to the other, 6 months apart, nearby stars appear to shift position relative to distant background stars. The parallax angle, measured in arcsecons, is inversely proportional to distance. A star with parallax of 1 arcsecond is at 1 parsec 3.26 light-years. The Gaia spacecraft has measured parallaxes for over 1 billion stars with unprecedented precision, extending reliable parallax distances to a few thousand light-years. Beyond parallax range, standard candles provide distances. Standard candles are objects whose intrinsic brightness is known, allowing distance to be inferred from observed brightness through the inverse square law. Cepheid variable stars, pulsating stars whose period of pulsation correlates tightly with intrinsic brightness, serve as standard candles up to approximately 100 million light-years. Edwin Hubble used cepheids to measure distances to nearby galaxies, establishing that they lie beyond the Milky Way and that the universe is expanding. The period luminosity relationship for Cepheids was discovered by Henrietta Leavitt in 1908 through observations of Cepheids in the Magellanic Clouds. Cepheids with longer periods are intrinsically brighter. By measuring a Cepheids period easy and apparent brightness easy, and using the period luminosity relation to infer intrinsic brightness calibrated from nearby Cepheids with parallax distances, astronomers calculate distance. The Hubble Space Telescope's key project in the 1990s used Cepheids to calibrate distances to dozens of galaxies, refining the Hubble constant. Type Ia supernovae are even brighter standard candles, visible across billions of light-years. These supernovae result from white dwarfs in binary systems accreting matter until they reach the Chandrasekhar limit, approximately 1 point for solar masses, and explode. Because they explode at a consistent mass, Type Ia supernovae have remarkably uniform peak brightness, making them excellent standard candles. Observations in the 1990s of distant Type Ia supernovae revealed accelerating expansion and dark energy. Calibrating Type Ia supernovae requires measuring distances to nearby ones using Cepheids or other techniques, establishing the intrinsic brightness. Then observing distant Type Ia supernovae and comparing observed brightness to inferred distance. Refinements account for variations in supernova brightness through light curve shape and color, improving standardization. With calibration, Type Ia supernovae measure distances reliably out to z approximately equals 1.5, corresponding to look-back times of approximately 10 billion years and proper distances exceeding 10 billion light-years. For even more distant objects, standard rulers provide distance estimates. Baroid acoustic oscillations, the imprint of sound waves from the early universe on the distribution of galaxies, provide a standard ruler approximately 490 million light-years in length in co-moving coordinates. This scale is determined from physics of the early universe and appears as a characteristic clustering scale in galaxy surveys. By measuring the apparent scale angular size of bow features in galaxy distributions at various redshifts, astronomers infer distances. Bow measurements extend to z approximately equals 2, tracing expansion history over approximately 11 billion years. Another distance indicator involves gravitational lensing. Massive objects like galaxy clusters bend light from background galaxies, creating multiple images or arcs. The geometry of lensing depends on distances between observer, lens, and source, allowing distance measurements. Time delays between multiple images of variable sources provide additional constraints. Gravitational lensing is particularly useful for constraining the Hubble constant and testing cosmological models. For the most distant objects, redshift combined with cosmological models infers distance. Measuring a galaxy's redshift is relatively straightforward. Obtain a spectrum, identify spectral lines, hydrogen, oxygen, etc. Compare observed wavelengths to laboratory wavelengths, and calculate z equals lambda underscore obs, lambda underscore emit, lambda underscore emit. Given redshift and a cosmological model lambda CDM with specified parameters, compute distance using the integral presented earlier. This method depends on model assumptions, but the lambda CDM model is well constrained by multiple independent observations. The cosmic microwave background provides critical constraints on cosmological parameters. The CMB's temperature and polarization fluctuations encode information about the universe's geometry, composition, and expansion history. The Planck satellite measured the CMB with extraordinary precision, determining the Hubble constant h is approximately equals 67 km per second mpc from Planck. Matter density omega underscore m approximately equals 0.32, dark energy density omega underscore lambda approximately equals 0.68, and spatial curvature consistent with flat omega underscore k approximately equals 0.00 plus or minus 0.05. These parameters, plugged into the Friedmann equations, predict the observable universe's size. However, a tension exists in Hubble constant measurements. The Planck CMB measurement yields h approximately equals 67 km per second mpc, while local measurements using Cepheids and Type Ia supernovae yield h approximately equals 73 km per second mpc. This approximately 8% discrepancy exceeds measurement uncertainties and is a subject of intense research. The tension could indicate systematic errors in one or both measurements, new physics beyond lambda CDM, or evolution of dark energy. Resolving this tension is a top priority in cosmology. The Hubble constant directly affects the calculated size of the observable universe. If h equals 67 kilometers per second mpc, the Hubble radius CH approximately equals 14,600 mpc, and the co-moving horizon is approximately 3.3 times this, or approximately 48 billion light-years, making the observable universe approximately 96 billion light-years across. If h equals 73 kilometers per second mpc, the Hubble radius is approximately 13,400 mpc, and the observable universe is approximately 88 billion light-years across. The difference is significant but doesn't change the fundamental conclusion. The universe is much larger than its age in light-years. Another constraint comes from Big Bang nucleosynthesis (BBN), the production of light elements in the first minutes after the Big Bang. The abundances of deuterium, helium-3, helium-4, and lithium-7 depend on the universe's boron density and expansion rate during nucleosynthesis. Measurements of primordial abundances combined with BBN calculations constrain cosmological parameters independently of CMB observations. BBN and CMB constraints agree. Validating the lambda CDM model. Gravitational wave observations provide an emerging distance measurement technique. Binary neutron star mergers, like GW170817 observed in 2017, emit gravitational waves whose amplitude and frequency evolution encode the source's distance luminosity distance. If the merger also produces electromagnetic counterparts gamma-ray bursts, optical transients allowing redshift measurement, combining gravitational wave distance and electromagnetic redshift provides an independent Hubble constant measurement. This standard siren method is in its infancy but promises to resolve the Hubble tension with future observations. The observable universe's size also depends on the universe's geometry. If the universe is positively curved closed, space curves back on itself, and the observable universe is smaller than in a flat universe. If negatively curved open, the observable universe is larger. Measurements from the CMB constrain curvature tightly, finding omega_k equals 0.00 plus or minus 0.05, consistent with flatness. A perfectly flat universe omega_k equals 0 has infinite total volume, though only a finite portion is observable. The observable region's size of 93 billion light-years applies to a flat universe. Curvature would modify this slightly. Measuring the size of the observable universe is thus a complex endeavor synthesizing data from stellar parallaxes, Cepheid variables, Typeus supernovae, boron acoustic oscillations, gravitational lensing, the cosmic microwave background, Big Bang nucleosynthesis, and gravitational waves. Each measurement technique carries uncertainties that propagate to the final result. Yet the convergence of multiple independent methods on a consistent picture of flat, expanding universe dominated by dark energy, approximately 13.8 billion years old and 93 billion light-years in diameter provides confidence in the lambda CDM model. The precision with which we know the universe's size is limited by uncertainties in the Hubble constant and other parameters. We know the observable universe is 93 billion light-years across to perhaps plus or minus 5%, accounting for parameter uncertainties. Improving precision requires better measurements of H's, better understanding of dark energy, and improved models of cosmic expansion. Future missions like the Nancy Grace Roman Space Telescope, Euclid, and next-generation CMB experiments will refine these measurements. The process of measuring the cosmos illustrates both the power of the scientific method building understanding through layers of interlocking observations and theory and the humility required. When studying the universe, we measure distances to objects billions of light-years away, track expansion over 13.8 billion years, and deduce the universe's size to percent-level precision, yet uncertainties remain. The Hubble tension reminds us that our understanding evolves, sometimes revealing surprises that challenge models. The 93 billion light-year observable universe is our best current answer, a number reflecting humanity's cumulative efforts to measure the cosmos and understand our place within it. The CMB horizon, the cosmic microwave background, represents the farthest back in time we can observe, the ultimate boundary of the observable universe in temporal terms. The CMB photons we detect today were emitted 380,000 years after the Big Bang, when the universe transitioned from opaque plasma to transparent neutral gas, allowing light to travel freely. The CMB defines our cosmic horizon not because nothing exists beyond it, but because earlier times our opaque photons scattered constantly off free electrons, preventing them from traveling long distances. Before 380,000 years, the universe was a hot plasma of protons, electrons, and photons in thermal equilibrium. Photons continuously scattered off free electrons through Thomson scattering, never traveling far before being absorbed and re-emitted. This made the early universe opaque, like being inside a glowing fog where light is omnipresent but visibility is limited. Any structure or events from this era cannot be observed through electromagnetic radiation because photons from that time did not propagate freely to us. At 380,000 years, the universe had expanded and cooled enough to about 3000 Kelvin for electrons and protons to combine into neutral hydrogen atoms, a process called recombination. With neutral atoms dominating and free electrons scarce, photon scattering ceased. The universe became transparent, and photons could travel unimpeded across cosmic distances. These photons, emitted from the last scattering surface, are what we observe today as the cosmic microwave background. The last scattering surface is not a physical surface but a spherical shell surrounding us from which the CMB photons we observe were last scattered. The radius of this shell in co-moving coordinates is approximately 46 billion light-years, essentially the same as the particle horizon because the CMB was emitted very early in cosmic history. Photons from the last scattering surface have been traveling toward us for 13.8 billion years in our frame, but due to expansion, the material that emitted them is now 46 billion light-years away. The CMB we observe today has been redshifted from the 3000 Kelvin blackbody spectrum at emission to a 2.725 Kelvin blackbody spectrum, a redshift of Z approximately equals 1100. This redshift corresponds to the universe being 1100 times smaller at recombination than today. The wavelength of photons has been stretched by a factor of 1100. Cooling the radiation from visible glowing like the surface of a red giant star to microwave wavelengths peaking around 1 to 2 millimeters. The CMB is remarkably uniform, with temperature variations of only about 1 part in 100,000 across the sky. This uniformity demonstrates that the universe at recombination was extremely homogeneous, supporting the inflationary model's prediction that our observable universe originated from a small, causally connected region. The tiny temperature fluctuations observed in the CMB, first detected by the COBE satellite in 1992, represent the seeds of structure, slightly denser regions that would grow through gravity into galaxies and clusters. The CMB's temperature fluctuations encode a wealth of information about cosmological parameters. The angular power spectrum of the CMB, which quantifies temperature fluctuations as a function of angular scale, shows a series of acoustic peaks. These peaks result from sound waves in the primordial plasma, oscillating before recombination. The positions and amplitudes of the peaks depend on the universe's geometry, composition, and expansion history. The first acoustic peak, around 1 degree angular scale, reflects the size of the largest sound wave that completed exactly one oscillation before recombination. This scale is determined by the sound horizon at recombination. The distance sound waves could travel in 380,000 years. The observed angular size of this feature, combined with its known physical size, allows determination of the universe's geometry. The fact that the first peak is at exactly 1 degree indicates the universe is spatially flat, as predicted by inflation. Higher peaks in the CMB power spectrum provide additional constraints. The ratio of odd peaks to even peaks constrains the baryon density ordinary matter. The heights of the peaks constrain dark matter density. The spectrum still constrains the spectral index of primordial fluctuations, testing inflation's predictions. The Planck satellite measured the power spectrum with exquisite precision, determining cosmological parameters to better than 1% precision in many cases. The CMB also carries information in its polarization. Thomson scattering polarizes light, and the pattern of polarization in the CMB encodes information about the velocity of plasma at recombination and about gravitational waves from inflation. The polarization is decomposed into E-mode gradient-like patterns and B-mode curl-like patterns. E-modes have been detected and provide additional constraints on cosmological parameters. B-modes from gravitational waves have not been definitively detected but remain a target for future experiments. The CMB horizon defines the limit of electromagnetic observations, but neutrinos and gravitational waves can in principle probe earlier times. The cosmic neutrino background, analogous to the CMB, consists of neutrinos decoupling from matter 1 second after the Big Bang when the universe cooled below approximately 10 billion Kelvin. These relic neutrinos, redshifted to low energies, permeate space but have not been directly detected due to their weak interaction with matter. Detecting the neutrino background would test Big Bang nucleosynthesis and early universe physics. Gravitational waves provide an even earlier window. Primordial gravitational waves generated during inflation would propagate freely through the universe, unaffected by matter. These waves would create B-mode polarization in the CMB and could be detected directly by gravitational wave observatories sensitive to ultra-low frequencies around 10 to 16 Hz. Detecting primordial gravitational waves would confirm inflation and measure the energy scale at which inflation occurred, a major goal of observational cosmology. The CMB's observation also provides a remarkable illustration of the universe's size. The photons we detect were emitted from gas 46 billion light-years away in current coordinates, yet the light has been traveling only 13.8 billion years. This is possible because the gas was much closer when it emitted the light about 42 million light-years away, and space expanded during the photon's journey, stretching the separation from emitter to observer. The CMB is observed in all directions with nearly the same temperature, indicating we are surrounded by a spherical last scattering surface. Every observer in the universe sees their own CMB sphere, centered on themselves. These spheres overlap partially for nearby observers but not at all for observers separated by more than 93 billion light-years. This observer-dependent horizon is a fundamental feature of cosmology, with no preferred center or edge in the universe itself. The CMB's uniformity across the sky initially posed a problem called the horizon problem. Regions of the CMB separated by more than about 2 degrees on the sky correspond to locations at recombination that were separated by distances larger than light could have traveled in 380,000 years. These regions were not in causal contact, they could not have exchanged information or thermalized to the same temperature. Yet they have nearly identical temperatures, differing by less than 0.01%. How? Inflation solved this by proposing that all observable regions were in causal contact before inflation, thermalized to the same temperature, then inflated to occupy our entire observable universe. The regions that appear causally disconnected at recombination were actually causally connected in the pre-inflation era. Inflation stretched these small causally connected regions to sizes much larger than the horizon at recombination, creating the observed uniformity. The CMB also reveals the universe's age independently of other measurements. The distance to the last scattering surface, combined with the redshift, constrains the expansion history. The acoustic peak's angular positions depend on the expansion rate integrated from recombination to today. Fitting the observed CMB power spectrum to models determines the universe's age, yielding T equals 13.8 billion years in close agreement with ages determined from oldest stars and radioactive dating. Future CMB observations will refine cosmological parameters and search for subtle signals. Experiments like the Simons Observatory and CMBS-4 will improve measurements of B-mode polarization. Probing inflation. Space missions may eventually observe the CMB at higher angular resolution and sensitivity. Revealing additional details about the early universe, the CMB will remain a cornerstone of cosmology, our oldest light and most distant electromagnetic horizon. The CMB horizon marks the limit of direct electromagnetic observation, but it is not a barrier to understanding earlier times. Theoretical models, constrained by observations, extrapolate back to the Planck epoch T-43 seconds, when quantum gravity effects dominate. While we cannot observe these earliest moments directly, their consequences inflation, the production of matter and antimatter. The formation of nuclei and Big Bang nucleosynthesis are observable in the CMB and in the universe's composition and structure. The CMB thus serves multiple roles. It is our most distant visible horizon, a baby picture of the universe at 380,000 years old, a constraint on cosmological parameters, evidence for inflation, and a reminder that the observable universe is both vast 93 billion light-years across and finite, bounded by horizons imposed by light speed and cosmic age. The CMB connects the universe's largest scales to its earliest moments, encapsulating in a nearly uniform 2.7 to 5 Kelvin glow the entire history of cosmic expansion from the Big Bang to today. Dark energy dominance. Dark energy, the mysterious component comprising 68% of the universe's energy density, plays a decisive role in determining the observable universe's size and future. Dark energy's accelerating effect on expansion means the universe is larger than it would be without dark energy, and it also implies that the observable universe will not grow indefinitely. Understanding dark energy is essential for understanding why the observable universe is 93 billion light-years across and what will happen to cosmic horizons in the future. Dark energy was discovered through observations of distant Type Ia supernovae in 1998. Two independent teams, the Supernova Cosmology Project and the High-Z Supernova Search Team, measured the distances and redshifts of supernovae at Z approximately equals 0.5 to 1.0. They found that these supernovae were dimmer than expected, indicating they were farther away than predicted by models assuming decelerated expansion. The only explanation consistent with the data was that the universe's expansion is accelerating, driven by a previously unknown component with negative pressure. Negative pressure is the defining property of dark energy. In general relativity, pressure contributes to gravity. Positive pressure, like in ordinary matter, adds to gravitational attraction. Negative pressure does the opposite. It causes gravitational repulsion, driving accelerated expansion. For dark energy to drive acceleration, its equation of state parameter W equals pressure or density must be W minus 1/3. The simplest model, the cosmological constant, has W equals -1 exactly, corresponding to constant energy density everywhere and always. The cosmological constant lambda was originally introduced by Einstein in 1917 to create a static universe solution to his equations. When Hubble discovered expansion, Einstein abandoned lambda, allegedly calling it his biggest blunder. Ironically, observations now support a non-zero cosmological constant as the explanation for dark energy. The cosmological constant can be interpreted as the energy density of the quantum vacuum. Though quantum field theory predictions for vacuum energy exceed the observed value by 120 orders of magnitude. The worst prediction in physics. Dark energy's dominance began approximately 10 billion years after the Big Bang. Z approximately equals 0.3, or about 4 billion years ago. Before this, matter dominated, and expansion decelerated. The transition occurred when the universe expanded enough that matter density diluted below dark energy density. Since dark energy density does not dilute, it eventually dominates in an expanding universe regardless of initial conditions, assuming dark energy is a cosmological constant. The effect of dark energy on the observable universe's size is subtle. If dark energy did not exist, and the universe were matter-dominated throughout, expansion would have decelerated continuously, and the observable universe would be smaller, perhaps 40 billion light-years in radius instead of 46.5 billion light-years. Dark energy's acceleration for the past 4 billion years means space has expanded more than it would have under deceleration, stretching the co-moving horizon slightly larger. More significantly, dark energy determines the future size of the observable universe. The cosmic event horizon, the boundary beyond which events happening now will never be observable in the future, is determined by dark energy. In a decelerating universe, the event horizon is at infinity eventually. Light from any event can reach us. In an accelerating universe with cosmological constant, the event horizon is at a finite co-moving distance. currently about 62 billion light-years. This means galaxies beyond 62 billion light-years right now are receding so fast that light emitted from them today will never reach us, even given infinite time. The observable universe will not grow indefinitely. As time progresses, the particle horizon boundary from which light can have reached us approaches the event horizon asymptotically. After infinite time, the particle horizon reaches approximately 62 billion light-years, defining the maximum size of the observable universe. Galaxies between the current particle horizon 46.5 billion light-years and the event horizon 62 billion light-years will eventually enter our observable universe as their light reaches us. However, by the time we see these galaxies, they will be highly redshifted, appearing fainter and older. Galaxies currently within our observable universe but beyond the event horizon will eventually disappear as they accelerate beyond our ability to observe new events in their evolution. Though we will continue seeing light emitted from their past, the nature of dark energy remains one of cosmology's deepest mysteries. Is it truly a cosmological constant with W equals -1, or does it evolve with time? If dark energy evolves, the equation of state parameter W might change, altering expansion's future. If W-1 phantom energy, expansion could accelerate so violently that it eventually tears apart galaxies, stars, planets, atoms, and even spacetime in a Big Rip scenario. If W becomes positive, expansion could reverse, leading to a collapse in a big crunch. Observations constrain W to be close to -1, with current measurements from supernovae and the CMB giving W equals -1, 3 plus or -0.03, consistent with a cosmological constant. More precise measurements are planned with upcoming surveys like the Dark Energy Spectroscopic Instrument DESI and the Nancy Grace Roman Space Telescope, which will observe hundreds of thousands of supernovae and map galaxy distributions across cosmic history, constraining W and its possible time evolution. Alternative explanations for dark energy include quintessence, a dynamical scalar field similar to the inflaton, but with much lower energy density. Quintessence fields can have time-varying W, unlike the cosmological constant. Modified gravity theories propose that general relativity breaks down on cosmological scales, with gravitational physics differing from Einstein's equations in ways that mimic dark energy. Distinguishing these possibilities requires observations sensitive to the expansion history's details and to the growth rate of cosmic structure. Dark energy affects structure formation. In a matter-dominated universe, gravitational collapse competes against expansion, and structures grow logarithmically with time. Dark energy's acceleration suppresses structure growth on large scales because it increases expansion rate, making it harder for gravity to pull structures together, the largest gravitationally bound structures, galaxy superclusters, formed before dark energy dominated. After dark energy domination, new large-scale structures cease forming. The impact of dark energy on galaxy formation is minimal because galaxies formed early when matter dominated. Within bound structures like galaxy clusters, dark energy is irrelevant because local gravitational binding vastly exceeds dark energy's repulsive effect. Dark energy operates only on large scales where structures are not gravitationally bound. This scale-dependent effect provides a test. Observations of structure growth constrain dark energy independently of expansion measurements. The coincidence problem asks why we live at the epoch when dark energy and matter densities are comparable. For most of cosmic history, either radiation or matter dominated overwhelmingly. Dark energy is significant only in a narrow window around the present epoch. In the past, dark energy was negligible. In the future, it will dominate completely. Why do we observe the universe during this special transition? This might be anthropic. Observers require complex structures like galaxies and stars, which form during matter domination. And we observe during the matter-to-dark energy transition because that's when observers exist. Dark energy connects to fundamental physics through the cosmological constant problem. Why is vacuum energy so small? Quantum field theory predicts vacuum energy from virtual particle fluctuations. Summing over all fields and frequencies up to the Planck scale gives a vacuum energy density approximately 10,120 times larger than observed. Cutting off at lower energies yields smaller but still enormous values. Understanding why vacuum energy is nearly zero but not exactly zero is a major unsolved problem in theoretical physics. The observable universe's size of 93 billion light-years reflects dark energy's influence in multiple ways. Dark energy's domination for the past 4 billion years contributed to the universe being slightly larger than without acceleration. Dark energy's future domination means the observable universe will not grow much larger, asymptotically approaching about 124 billion light-years in diameter after infinite time. The current size, intermediate between the matter-dominated prediction approximately 80 billion light-years and the far future limit approximately 124 billion light-years, reflects the transition era we inhabit. Dark energy also affects the cosmic microwave background through the integrated Sachs-Wolf effect. Photons traveling through evolving gravitational potentials gain or lose energy. In a matter-dominated universe, potentials decay slowly. With dark energy, potentials decay faster during dark energy domination, imprinting a subtle signal on CMB temperature fluctuations at large angular scales. Observations of this effect provide independent evidence for dark energy from the CMB. The future of the observable universe depends entirely on dark energy. If dark energy remains constant, cosmological constant, the universe will expand forever, cooling and diluting, with galaxies beyond our local group eventually receding beyond the cosmic horizon, leaving our descendants in an island universe surrounded by darkness. Stars will exhaust their fuel, galaxies will fade, and over 10,100 years or more, even black holes will evaporate through Hawking radiation. The universe will approach maximum entropy, a cold, dark, nearly empty state called heat death. Alternative dark energy models yield different futures. Phantom energy leads to Big Rip, possibly within tens of billions of years. Decaying dark energy could lead to Big Crunch. Cyclic models propose the universe undergoes repeated expansions and contractions, with dark energy's role varying across cycles. Observations over the coming decades will constrain dark energy's properties, revealing whether the universe's fate is eternal expansion, cataclysmic rip, recollapse, or something more exotic. Understanding dark energy is understanding the universe's destiny, and the observable universe's size is an interim snapshot of a cosmos shaped by this mysterious dominant component. Beyond the horizon, the observable universe's edge at 46.5 billion light-years is not a physical boundary but a horizon imposed by the finite speed of light and the finite age of the cosmos. Beyond this horizon lies more universe, potentially infinite in extent, filled with galaxies, stars, and structures we cannot observe because light from them has not had time to reach us. Understanding what lies beyond the observable universe requires distinguishing between the observable universe and the entire universe. A distinction raising profound questions about cosmology and the nature of reality. If the universe is infinite, as inflationary models suggest it might be, then the observable universe is an infinitesimal fraction of the whole. An infinite universe contains an infinite number of galaxies, stars, planets, and potentially even observers. Every possible configuration of matter within the constraints of physical law, no matter how improbable, occurs infinitely many times in an infinite universe. This includes exact duplicates of our observable universe, our galaxy Earth, and even you, existing in regions trillions of light-years beyond our horizon. The likelihood of duplicates can be estimated statistically. The observable universe contains approximately 1,090 particles. The number of distinguishable quantum states these particles can occupy is finite though vast, roughly 10,120 states within the observable region. If the universe is infinite and approximately uniform, every possible state occurs somewhere, and the typical separation between identical regions is about 10,120 times the observable universe's size. This distance is incomprehensibly large, but in an infinite universe, such duplicates exist. Alternatively, the universe might be finite but unbounded, curved back on itself without edges like the surface of a sphere or a torus. In such a topology, traveling far enough in any direction returns you to your starting point, though the return journey would take longer than the universe's age. A finite and bounded universe would contain a finite number of galaxies and particles, and its total volume could be calculated if we knew the curvature. Current observations constrain curvature tightly, requiring any finite and bounded universe to be much larger than the observable universe. At least several times 93 billion light-years in circumference. Inflationary cosmology predicts the universe extends vastly beyond the observable region. Inflation expanded a microscopic region to macroscopic or even light-year scales. Our observable universe, 93 billion light-years across, originated from a region perhaps a few centimeters in size after inflation. If inflation expanded space by a factor of 1026 or more, the total inflated region could be 1026 times larger than observable, or more. This inflated region might be effectively infinite, extending forever beyond our horizon. Eternal inflation complicates the picture further. In many inflationary models, inflation does not end everywhere simultaneously but rather ends in localized regions called bubble universes while continuing elsewhere. These bubbles, including our observable universe, are embedded in an eternally inflating background. The eternally inflating space expands exponentially forever, continually producing new bubble universes. This creates a multiverse of bubbles, each potentially with different physical properties determined by how inflation ended in that bubble. If eternal inflation is correct, the universe beyond our observable horizon consists partly of more space similar to ours within our bubble and partly of other bubbles with possibly different physics. The space within our bubble might extend trillions of light-years or be infinite. Beyond our bubble lies the inflating space and other bubbles, forming a vast multiverse structure. Whether this multiverse is observable even in principle is debated. Most argue it is not, making it philosophically contentious. Observations provide hints about the universe beyond our horizon. The CMB's uniformity suggests the universe is similar on scales much larger than observable. If the universe beyond our horizon were drastically different, we might observe gradients or anomalies in the CMB. The lack of such features implies homogeneity extends beyond the observable region. The universe's flatness also suggests it is much larger than observable, since curvature would be more apparent if the universe were only slightly larger than our observable region. Another clue comes from the universe's topology. If the universe has a closed topology finite but unbounded, we might detect repeating patterns in the CMB or galaxy distributions if the universe is small enough that light has circumnavigated it. Searches for such patterns have found none, implying that if the universe is closed, its circumference exceeds several times the observable diameter. An open or flat topology is consistent with infinite spatial extent. The question of what lies beyond the horizon also connects to the multiverse hypothesis in other contexts. String theory suggests our vacuum state is one of perhaps 10,500 possible vacua, each with different physical constants and particle properties. If different regions realize different vacua, creating a landscape of universes with varying properties, then beyond our horizon might lie regions where physics is fundamentally different, a different mass. As for particles, different strengths for forces, different dimensionality of space. Such a multiverse is philosophically controversial because it may be untestable. If we cannot observe other vacua, any theory predicting them makes no falsifiable predictions. Some argue this renders the multiverse unscientific. Others argue the multiverse is a consequence of well-motivated theories inflation. String theory and should be taken seriously even if not directly testable. The debate continues. With no consensus, the observable universe's boundary is not static. As time progresses, the particle horizon grows, bringing new regions into view. Light from galaxies currently beyond our horizon will eventually reach us, making them observable. However, due to accelerating expansion, the particle horizon approaches the cosmic event horizon asymptotically. After infinite time, regions beyond about 62 billion light-years will never become observable, defining a maximum size for the observable universe. This means galaxies currently visible will eventually disappear beyond the cosmic event horizon. As they accelerate away, their light becomes increasingly redshifted, eventually shifting beyond any observable wavelength. New photons emitted from these galaxies will never reach us, so we will see them freeze in time. Asymptotically approaching infinite redshift, the observable universe will empty, leaving only our local gravitationally bound group of galaxies. The concept of beyond the observable universe also raises questions about simultaneity. In relativity, simultaneity is observer-dependent. When we ask what exists right now beyond our horizon, right now is ambiguous. Different observers moving at different velocities would define different simultaneity surfaces, each including different regions beyond the horizon. There is no objective present moment extending across space, complicating the question of what exists beyond the horizon at this instant. Despite these conceptual challenges, cosmologists confidently assert that the universe extends beyond the observable horizon, likely filled with similar galaxies and structure, and possibly infinite in extent. This assertion rests on the cosmological principle: the universe is homogeneous and isotropic on large scales, with no privileged locations. If the observable universe contains 2 trillion galaxies, the region beyond likely contains more galaxies, stars, and planets, statistically indistinguishable from what we observe. The implications for life are staggering. If the universe beyond our horizon contains similar structure to the observable universe, it contains countless planets, potentially billions of habitable worlds, and possibly civilizations. Some might be technologically advanced, asking the same questions we ask about what lies beyond their horizon. These civilizations are forever beyond our causal contact if they lie beyond the cosmic event horizon, making the universe far vaster and more populated than the observable region suggests. The universe beyond the observable horizon also includes the universe's past light cone intersecting regions we will never see. Light from these regions could have reached Earth in the past or could reach us in the future, but it cannot reach us now. These regions are causally disconnected from us at present, but will be connected. The full causal structure of spacetime is complex, with observable and unobservable regions shifting as time evolves. Philosophically, the existence of an unobservable universe challenges naive empiricism, the idea that only observable entities are real. Most cosmologists accept that the universe beyond our horizon is real, even though it cannot be observed directly. This acceptance rests on the explanatory power of theories like inflation and general relativity, which predict the existence of unobservable regions as consequences of observed phenomena. The unobservable universe is a theoretical inference, not a direct observation, but it is an inference with strong justification.